Hello everyone, and welcome to our video on polar coordinates. So let's go ahead and just get right to it. So we're talking here about an alternative coordinate system that we call polar coordinates. So rather than using x and y axis coordinates, we will define a point's location by an angle and a distance. So as a convention, when using polar coordinates, we refer to the origin, the point 0, 0 in the Cartesian plane, as the pole, and the x-axis as the polar axis. So we've got a little diagram here, right? So we've labeled the positive x-axis here as the polar axis. Here's our angle theta. Here's our length r. And so what we see is that this point P is now defined by its distance r from the pole and the angle theta, formed between the polar axis and this point O to P. So all this is saying is, this is just as good as having an x and a y coordinate. If we just know the angle at the origin and how far out to go, it'll give us an exact position for the point. Now the ordered pair r theta represents the point P, and r and theta are called the polar coordinates of P. So the standard convention is that positive angles of theta are measured counterclockwise from the polar axis. So same way we've always dealt with standard angles in trigonometry. And additionally, if r is negative, then we consider the point P as pointing the opposite direction from theta. So if we look at this example diagram here, if we've got an angle theta and our point is negative r theta, then we look in the direction theta, but because r is because this first coordinate is negative, we go opposite of that angle when drawing our distance. Now, one thing I'd like you all to notice now, before we get on to some examples, is notice that the point negative r theta represents the same point as r theta plus pi, because if I took my angle theta and I just added pi to that angle, then that puts me at the same place here, except now my radius can travel positive in the actual direction of the angle. Okay, so let's look at a couple examples here. Plot the point whose polar coordinates are given, then find two other pairs of polar coordinates of this point, and one with r greater than 0 and one with r less than 0. Okay, so let's start by plotting the point. So we'll draw a little coordinate plane here. Now, we've got the angle 7 pi over 4, so I'll draw that first. 7 pi over 4 puts us here. And the radius is 1, so let's draw some marks 1 in each direction, right, just to get a distance here. Well, we're polar, so I don't really need to mark it -1. And let's just draw a little dotted line to represent the circle with radius 1 there. So if I want the point 1, 7 pi over 4, I'm looking at this intersection point where the circle of radius 1 intersects with the angle 7 pi over 4. So this here is my point. Okay, so now I'd like to find two other representations for that point. So the first one that's the easiest to do, I think, is to just look at the negative angle here. This is negative pi over 4. And if we go the same distance of 1, that takes us to the same point. So an equivalent point here is -1, or sorry, +1, negative pi over 4. Okay, now we would like one where the radius is negative. So in order to make the radius negative, I need to make the angle go in the opposite direction. So we'll put an angle right here. And so this purple angle will be 3 pi over 4, right? It's pi less than 7 pi over 4. So that puts this at -1, 3 pi over 4, because in this case, if we're pointing in the direction of 3 pi over 4, we would have to travel backwards to get to the point P here. Okay, so let's do another similar example here. This time we're going to go out a distance of 3. So I'll draw the circle with radius 3. And the angle pi over 6. Now here's the tricky part. So this is our angle pi over 6. We would like the intersection between our radius and our angle, but this time r has been labeled as negative. So that's a little different. So that means we've got to put our point out in the opposite direction. So that's going to put P back here. Okay, so there's our point. Now let's find 2 other ways we can represent that point. The first way is we could take this angle, and instead of going to pi over 6, we could take the larger angle here. That's pi plus pi over 6, so that's 7 pi over 6. And so that point would be 7 pi over 6. Got my coordinate backwards there. Let's try that again. That'll be my 7 pi over 6 for the angle. And then in this case, since the angle is pointing in the same direction as the point, we'll have a positive 3 for the radius. Now, if we'd like another version of this point with a negative radius, we could get that by taking the negative angle. So from here and rotating backwards. And the negative angle that's coterminal there is negative 11 pi over 6. And we can get that by just taking negative 2 pi plus pi over 6. So this point would be negative 3, negative 11 pi over 6. Okay, so now let's take a look at the trigonometric relationship between polar and Cartesian coordinates. So what do we notice here? If I'm looking at an angle and a radius r, that point would have the Cartesian coordinates here x, y on this diagram. And so what do we know? We know that cosine of theta, by definition, is x over r, right? It's that adjacent side divided by the hypotenuse. And therefore, x is equal to r times cosine of theta. Likewise, sine of theta is y over r, and so y equals r times sine of theta. We also get that r squared is equal to x squared plus y squared from the Pythagorean theorem, and tangent of theta is equal to y over x. So just to add to this, that means that you can, if you know x and y, you can find r by taking the square root of x squared plus y squared. And if you know y and x, you can find theta by taking tangent inverse of y over x. Okay, so let's put this stuff to use and try to find some equivalent Cartesian coordinates. So we're given polar coordinates here, and we're going to convert them to Cartesian coordinates. Okay, so what do we know? We know that x is equal to r times cosine of theta. So for part A here, that gives me negative root 2 times cosine of 5 pi over 4. But cosine of 5 pi over 4 is the negative root 2 over 2. So those negatives cancel, and I get 2 over 2, which is 1. And so y is r times sine of theta. That's negative root 2 times sine of theta, which is sine of 5 pi over 4. That's negative root 2, and sine of 5 pi over 4 is also negative root 2 over 2. So that's also 1. So the Cartesian coordinates for this would be 1, 1. And then for the second point here, we get x equals, and r is 1 times cosine of 5 pi over 4. So that's just going to be negative root 2 over 2. And y is 1 times sine of 5 pi over 4, which is also negative root 2 over 2. And so our point would be negative root 2 over 2, negative root 2 over 2. And one thing I'd like to point out here is that generally speaking, Cartesian coordinates are unique, at least down to rationalizing and simplifying the expressions, right? Obviously, you could write 1 as 2 over 2, 2 over 2. That would be silly. But other than that, beyond simplification, they're generally unique to for each point on the Cartesian coordinates. But if we look at this previous example, what did we notice? We're noticing here that the Cartesian representations for a point are not unique. And as you'll see, that can make things a little bit tricky with functions in the Cartesian plane, because you won't get the same uniqueness of points, so your function can overlap on itself, but actually have different angles for the same point. So we'll see that later on. But for now, let's find equivalent polar coordinates with theta between 0 and 2 pi, and one with r greater than 0, and a second with r less than 0. Okay, so, well, again, what do we know? We know that r is the square root of x squared plus y squared. So for problem A here, take the square root of 3 times the square root of 3 squared plus 3 squared. That's the square root of, okay, 3 squared is 9. The square root of 3 squared is 3. 9 times 3 is 27. Plus 3 squared is 9. So altogether, that's the square root of 36, which is 6. Meanwhile, theta is tangent inverse of y over x. That's tangent inverse of 3 over 3 root 3. That's tangent inverse of 1 over root 3. And in this case, this is one we actually, if we know our unit circle well, we can figure out without having to touch a calculator. So we could say tangent of theta would then be 1 over root 3. But remember, tangent is sine of theta over cosine of theta. So if I think what values for sine and cosine together would simplify to 1 over root 3, that would be 1/2 divided by root 3 over 2. So that tells me that theta, the angle I'm looking for here, should be pi over 6. So one representation for the point is r, which is 6, and theta is pi over 6. And we'd like one other representation where the radius is negative here instead of positive. So it's going to be easiest if I just draw that. So we'll draw that. So we've got this angle pi over 6 here. We're going out a length of 6. Come on. Sorry, the pen's not working there for a second. So we're going at a length of 6. This angle is pi over 6. So I want another angle from 0 to pi over 2. So I'll spin out to this angle here, the opposite angle. And that's going to be pi plus pi over 6. So that's 7 pi over 6. So my second point would be negative 6, 7 pi over 6. Because again, if we go to this opposite angle here, when we head backwards, and that angle is kind of poorly drawn, it should look more like this. There we go. If we head to that opposite angle and draw backwards, then we're going to end up at the same place. So we make our radius negative there. Okay, back to part B here. And it's the same thing. R equals the square root of 1 squared plus negative 2 squared. That's the square root of 5. And theta equals tangent inverse of negative 2 over 1. That's, of course, just tangent inverse of negative 2. Now, tangent inverse of negative 2 is not one that I would know an exact angle for on the unit circle. I wouldn't expect anybody to. But we can use our calculator to approximate the angle here. So make sure that you're in radians, because we always default to radians when we're working with calculus. So make sure your calculator's in radians. And we get approximately, for tangent inverse of negative 2, negative 1.11 in radians. So if that kind of helps us draw this point on our graph a little bit. So it tells us we're going in the negative direction. And remember, pi, the straight angle, is 3.14. So this is about a third of that in the negative direction. So it's pretty close to a third of pi. It's not exactly, but close enough to draw the angle. So this is theta equals negative 1.11. And then the radius, of course, is square root of 5. So if I want another point but this time where the angle is between 0 and 2 pi, well, let me rephrase that. I want both points to have angles between 0 and 2 pi, but tangent inverse doesn't give me that. So because tangent inverse here gives me a negative angle, but we can find those angles by just analyzing the graph. So if I was to go to the opposite angle here, all right, what's this angle? It's theta equals pi minus 1.11. Or if we were being really more accurate, we would say pi minus tangent inverse of negative 2. And so that tells me one of my points would be negative root 5, and the angle pi minus tangent inverse of negative 2. And now I want one other angle that's between 0 and 2 pi, so I can look at the angle that rotates all the way out to here, right? And so that's pi, 2 pi. That's like going 2 pi and subtracting the 1.11. So this angle would be 2 pi minus 1.11. And that one would have a positive radius. Okay. Let's move on. So now we're going to try to figure out how to sketch curves in polar coordinates. So curve sketching in polar coordinates can seem a little tricky at first, but if you're really systematic with how you do things, then you'll get the hang of it before too long. Now, this example is relatively simple. We've got a constant function, r equals 3. So sketch the curve r equals 3. Well, that just means that the radius for every point on your curve is 3. So we go out to 3. And we'll draw a nice circle at 3. And that's it. That's r equals 3, because this function, r equals 3, means the set of all points with distance 3 from the origin, or from the pole, when we're talking polar coordinates. Now, example 5 here, sketch the curve theta equals 7 pi over 4. Well, we find the angle 7 pi over 4. So here's our angle. Now, this equation, theta equals 7 pi over 4, means all points that lie on that angle, 7 pi over 4. So all of the positive radius points would go in this direction, and whenever the radius was negative, it would go in this direction. And so what do we see? We see that if we have theta equals a constant for our equation, we get a straight line that passes through the pole. Okay, so now let's move on to something a little more complicated. Sketch the curve r equals cosine of 2 theta. So the first thing is I'm going to think about what the largest and smallest values for r can be. So since r is cosine of an angle, that means the largest value it can be is 1, and the smallest it can be is -1. So I'm going to just mark out 1 in each direction. And we're going to do a nice little circle here for all of the points that are at that distance of 1. This is not the graph of my curve. This is just going to help me graph my curve. So this line is r equals 1. And now we got to start thinking about angles, right? So first thing we want to think about is what happens at theta equals 0. Well, that would give me cosine of 0, which is 1. And so I'm going to extend that, though. So that gives me my starting point, but I actually want to think about all of the places where cosine of 2 theta equals 1. So I know this first point on the graph is going to be angle theta is 0, and the radius is 1, so it puts me right there. But where else is cosine of 2 theta equal to 1? Well, that's when 2 theta is, yes, 0, but also at 2 pi and 4 pi and so forth and so on. So that would be whenever theta is 0, pi, 2 pi, or so forth and so on. All I've done here is divided out that 2 across all of my solutions. And we're not going to plot any more of the curve yet. Instead, we're going to think about what kind of happens next. So where's the major points for a cosine and sine function is when cosine is 1, 0, or -1. So let's now look at when is cosine of 2 theta 0? Well, that's going to be when 2 theta is pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, so forth and so on. And if we divide all of those solutions by 2, we'll get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. All right. And finally, let's look at when cosine of theta is -1. That's when, or cosine of 2 theta is -1. That'll be when 2 theta is pi, 3 pi, 5 pi, so forth and so on. And one thing you'll notice is that I'm usually going to stop for any of these cosine and sine functions when I get to 2 pi, because generally at that point you're just going to start repeating values. What I mean when I get to 2 pi is when the angle we solve for gets to less than 2 pi, right? We're trying to draw a full circle of this thing from 0 to 2 pi. So that's about how far we need to go, usually. But not all functions work exactly the same, so we have to adjust that on a case-by-case basis. Okay, so now I'm going to go through and start drawing some of the angles that we're concerned with here. So we've got the angle 0 already. We're going to need the angle pi over 4. We've got pi over 2 up here. We're going to need 3 pi over 4. And then we've got pi over here. And then we also need 5 pi over 4. And then over here, we've got 7 pi over 4. So now we'll start plotting some points. So we already plotted the 0, 1 point. Now, when our angle is pi over 4, our R value should be 0. So that means when I swing out to this angle pi over 4, my point has to go down to 0. The distance from the origin is 0. So now we got to fill in what happens in between. So what do we see? R is going from 1 down to 0 as the angle is changing, right? So if we took little angles in here, gradually the distance is shrinking to 0. And I'm going to get rid of those extra angle marks because they do clutter up the image a little bit. But I'm trying to at least make the idea as clear as possible. All right. So at cosine of pi over 4, we had 0 for r. Now we look at cosine of pi over 2. We should get -1. So this is where it gets a little trickier, because I'm now looking at what happens in this section of the graph from the angle pi over 4 to pi over 2. But my radius is now negative between there. So I'm actually looking at what happens in the opposite region where the radius is negative. So I should get at the angle pi over 2, -1 for r puts me down here. And my radius is going out towards that -1 value from the origin, from the pole. Now we go to 3 pi over 4. R should be 0 again. So look, but this time we're now looking at this angular region from pi over 2 to 3 pi over 4. But again, our radius is still negative, so we're actually graphing in the region opposite of that. So if I'm going from this -1 to 0, that's going to rotate down there. What in the world just happened? Let's try that again. There we go. Okay, now we're looking at what happens at pi. So again, we're concerned with how the function travels from 3 pi over 4 to pi. So at pi, we should get 1. So we're going out a distance of 1. So it's rotating through that region to there. Okay, now we're looking at what happens in this region. And now, what do we have next? 5 pi over 4 gives me 0. So when I get to the angle 5 pi over 4, my graph has to shrink down to 0. Okay, and now we look at the next region. Okay, so now we're looking at the angle 3 pi over 2. And now I should get -1. So 3 pi over 2, I should be going in the negative direction. And so my radius here should be going negative for the whole region. So I'm in the opposite region again. It looks like that. Now I'm looking at this region of angles. My radius is still negative, so I'm actually drawing in the opposite region. And now I'm going down to 0 at 7 pi over 4. So we get to the angle opposite of 7 pi over 4, and it goes to 0. And now look at this, we've almost come full circle. We're at our last region here, and the radius at 2 pi is going to be 1. So this comes out from the pole back to there. Now look, what's obviously going to happen if we start drawing more regions is this point is just going to move along that same graph and repeat. So there's no need to continue drawing after that point. So hopefully you understood how we followed that graph piece by piece, but now let's actually look at a nice version of this graph and kind of summarize what we just saw here. So here I've got this in red. Here is the outline of the r equals cosine of 2 theta function. Now what's going to happen is as I change this slider, it's going to show us how this graph is drawn, and it's going to follow the corresponding point on the graph, and then this black line here is the angle that corresponds to theta. So we can follow this through. We see we get to, here we get to pi over 4. We got back to the origin. And now, remember, after pi over 4, the radius went negative. So now look, it starts drawing in the negative direction. When we got to pi over 2, it's still negative. Now back at 3 pi over 4, we pass through the pole again. And then we just keep going. And that's 2 pi. And notice, if we keep tracing through towards 4 pi, we just trace back over the graph again. Okay, hopefully that helps you visualize what's going on here a little bit. Now let's move on and do another similar kind of graph. So now we're going to sketch the curve r equals sine of 3 theta. So we're going to use the same basic thought process. First, I'm going to check what happens at 0 so that I know my starting point. So if theta is 0, r is sine of 0, which is 0. So my first point when theta is 0 is just at the origin. All right, what else do I need to draw? I need to draw what my maximum radius would be. And the maximum radius is 1, so we'll just put some marks for 1. And we'll draw a dotted circle so that we put those points at the right distance. Okay, and now I'm going to say, well, I don't want to just know when, I don't want to go through every single angle. That's not super practical, right? We just want to plot the necessary key angles. So let's say, well, when is sine of 3 theta 0, period? What are all the places where r will be 0? Well, it's going to be whenever 3 theta, whenever the angle is 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc. All right, and I stopped at 6 pi because 6 over 3 is 2, right? So we divide out that 3. We get 0, pi thirds, 2 pi thirds, pi, 4 pi thirds, 5 pi thirds, and 2 pi. All right, and now let's consider when is sine of 3 theta going to be 1? Because I do know that for when I start at 0 and I start increasing my angle, sine starts increasing towards 1. So when is this thing going to be 1? Well, that's going to be when 3 theta is pi over 2. Or if I add 2 pi to that, which would make it 5 pi over 2, or 9 pi over 2, or 13 pi over 2. And that's bigger than, when I divide by 3, that'll be bigger than 2 pi, so stop there. So that gives us pi over 6, gives us 5 pi over 6, or pi over 2, or sorry, 3 pi over 2 if I divide by 3. And then this would be 13 pi over 6. And finally, when is sine of 3 theta going to be equal to -1? Well, that's when 3 theta is at 3 pi over 2. Or add 2 pi to that, that's 7 pi over 2. Or 11 pi over 2. And again, we could stop there. Anything beyond that will be bigger than 2 pi. So this is pi over 2, 7 pi over 6, and 11 pi over 6. Now let's start plotting those points. So we already have our initial point at theta is 0, r is 0. Now when theta is pi over 6, we get 1. So let's draw the angle pi over 6. And so we should be at the point pi over 6 and 1. And so when I'm going through this region, it's got to be increasing the length as the angle rotates out. And now, when do we get, let's see, where was I? We went out to 1. Oh, when do we get 0 again? Well, we get 0 back at pi over 3. So we'll draw our angle pi over 3 here. Okay, now it starts getting tricky again because now our next value for r is going to be -1 at pi over 2. So now we'll start keeping track of our regions again. So now remember, we're drawing for this region, but the radius is negative. So I'm actually drawing opposite of that, right? And so at pi over 2, I should have a -1 radius. And so my graph rotates through that portion. And now my next angle, that was pi over 2. The next angle is going to be 2 pi thirds. So that's over here. So that's our region, is this region here. But again, our radius is still negative. So we're actually drawing in the region opposite of that. So we take our point here, we go down to the 0, 0 from there. Now, our next point, our next angle is at 5 pi over 6. And so finally, we're going in the positive direction again. So for this next region here, we're actually traveling in the positive direction. So we're going to go to pi 1. So here's the angle, not pi 1, 5 pi over 6. That was silly of me. Let me fix that. Sorry, the next angle here is 5 pi over 6. So that should be right about here. Okay, so this is our region. And our radius is positive, so we're actually drawing in that region. And then when we go to pi, or what's our next one? Yeah, pi, we're going to be back at 0. So it looks like that. Okay. And I drew an extra point there. Let's get rid of that. Okay, there we go. So little tricky. And this one you see it's kind of askew where the angles don't line up quite as nicely as the last example did. But one thing that I'd like to point out before we take a look at the graphs more closely is notice that in this example we had cosine of 2 theta and we had 4 petals, so twice as many. And here for sine of 3 theta, we actually had the exact same number of petals. And that is going to be true whenever you have r equals cosine of n times theta or sine of n times theta. Whenever you have an even number, you will get double the number of petals. Whenever you have an odd number, you'll get the exact same number of petals. So let's take a look at our graphing again. So we'll take a look at this graphing calculator again and see if we can kind of understand why that happens. So here, this is the graph for sine of 3 theta. It's just like that one I made for cosine. Same basic idea. We're tracing the point. Now notice I've changed my range from a is from 0 to 2 pi. So notice what happens when I get to pi here. The way this graph lines up, it ends up restarting because we end up having a negative range of r values in this region of angles here. So notice this theta is going here. So here's my angle theta. The r values are negative here, and because of the way it lines up, it ends up going back over one of the previous loops. So from 0 to 2 pi, we actually go through those loops twice. Whereas if we look back at our previous graph, so here I had it from 0 to 4 pi, let's change it to 2 pi. So now notice as we rotate through, when we get to pi, we actually are back to having a positive radius here. So we end up going opposite of this angle and into a region that we haven't rotated through yet. So this obviously is just a visual demonstration of what's going on. This is not a rigorous proof, but it is true in general that if you have an even number times theta in just sine or cosine. Now, if the function adds anything to it other than just sine of n times theta or cosine of n times theta, this doesn't apply. But if it is just those functions, then if n is an even number, you will double that, and that'll be the number of petals you end up with. And if it's an odd number, it'll just be the number itself. Now, this isn't going to really help you graph the function, because you need to know where to put those petals, but it will help you determine if your graph is correct at the end. You might have a better idea of whether or not your graph makes sense if you check the number of petals. Okay, let's go through and do a little bit more. So example 8, identify the curve by finding a Cartesian equation for it. So in this case, we've got theta equals pi thirds. So it's actually going to be easiest if we graph this thing first. So if I draw the angle pi over 3 here, all right, then what is this curve? It's the straight line that goes through that angle in both directions for positive r and negative r. And what is the slope here? So this is y, this is x, this is theta. Its tangent of theta is the slope of the line, right? So the slope of the line is tangent of pi thirds, which is sine of pi thirds divided by cosine of pi thirds. So altogether, that's the square root of 3 over 2 divided by 1/2, which is the square root of 3. And my equation is y equals mx plus b, but my intercept for the y-intercept for the Cartesian equation is 0. So this is just the square root of 3x. So this is the line passing through the origin with slope square root of 3. Okay, let's graph something else. R equals 1 plus 2 cosine of theta. All right, well, cosine of theta, again, my main concern is where is cosine of theta 1? Where is it 0? Let me write that a different way. Cosine of theta is 1, but what does that tell me about r? Well, if cosine of theta is 1, then r is 1 plus 2 times 1, which is 3. All right, so theta, when does that happen? That happens at theta equals 0 and 2 pi. And since the period of cosine is 2 pi, I can just stop there. Okay, what about when is cosine of theta 0? Well, when cosine of theta is 0, if we look at this equation, 1 plus 2 times cosine of theta, that would be just 1, r equals 1. And which angles does that happen at? That's pi over 2, 3 pi over 2, and so forth. And finally, cosine of theta equals negative 1. What will that make r be? So 1 plus 2 times negative 1, that's negative 1. And that's going to be when theta is at pi. And the next time would be 3 pi, but that's too big. We're not worried about that. So now I know that my radius is going to be one of these three values, negative 1, 1, or 3. So let's draw a circle with radius 1. And a circle with radius 3. And that'll make it a lot easier to keep track of our graph. So a couple reasons why I really suggest that everybody go through the trouble of drawing out these circles for your different radius, radii, and the lines for your angles is because it's going to make it both easier for you to keep track of what you're doing, but also easier for someone to interpret what you're drawing. Because if you look, my graph is not a perfect circle, and nobody's going to draw that perfectly. But if you at least have this diagram in place, then a person who's viewing it can more easily interpret what you meant to be there. Now, as far as the angles, all the angles in this case are the quadrantal angles. So we're just looking at 0 and pi over 2 and pi and 3 pi over 2 and 2 pi. Okay, so when theta is 0, r should be 3. That puts my first point out here. And then my next point is at pi over 2. So when theta is pi over 2, r should be 1. That puts the point here. So my graph has to rotate through here. Now, when theta is pi, I get negative 1 for cosine. That actually suggests that I might want one other angle figured out here. So if I'm going from a radius of 1 to a radius of negative 1, I might want to do the extra work to figure out where is r 0. Since it didn't come up in those standard angles, we can solve for it. So that gives me cosine of theta is negative 1/2. So theta, from 0 to 2 pi, cosine would be negative 1/2 at 2/3 of pi and 4/3 of pi. So 2/3 of pi, that's going to put me about here. And 4/3 of pi puts me here. Okay, so that tells me the next angle I actually want to look at isn't pi. It's actually 2/3 of pi. My radius is going to go down to 0 there. And then for the angle pi, my radius is actually going to be -1. So it's actually rotating. Now by the way, we're at this. Hold on, my picture does not look good here. I'm going to try to fix it and make it look better. Okay, I got down to 0 at this angle. Now, for this region here, my radius is now going to be negative. And it's heading towards -1 at pi. So I'm looking at the region opposite of this. And so my radius is negative and rotating through there. Now I look at this next region here. And at 4 pi thirds, I'm going to get 0 again. So I'm going, but again, remember I'm negative, so I'm actually in the opposite region, the mirror image. Okay, now I'm in this region. And remember, so we've done pi, we've done 4 pi thirds. So now we're at 3 pi over 2, and the radius is now 1. So it's coming out of this origin out to 1. And now we're going all the way out. The last thing we got left is 2 pi, where the radius is 3. And so this is going to finish rotating out to there. Okay, well, we're making progress here. By the way, we often call shapes similar to this cardioids, though a lot of times the typical cardioid will just doesn't have the negative region, but I think these are still also considered cardioids, even though they have that negative loop inside. Okay, now, here's a weird one to graph r equals ln of theta. And it's for theta greater than or equal to 1. So if theta is 1, that's about 1/3 of pi, a little less than 1/3 of pi. And ln of 1 is 0, so at that angle, we're here. And I'm going to draw a couple circles as kind of guidelines. But the reality is, this one, you're just going to have to, you're only going to really be able to get a rough sense of what this graph looks like without using some sort of graphing tool. But we can still do that. We can think through the graph, plot a few points, and understand the general idea of what this graph is doing. So in this case, the natural log isn't defined, based on angles, so we don't have nice angles to evaluate it at. So we're going to, start at 1 and start plugging in some other angles. So let's try ln of pi. And we'll just plug that into our calculator. And ln of pi is about 1.15. So when I get to the angle pi over here, I should have something that's a little bit bigger than 1. So my graph is extending out from 0. As it rotates around, it's extending out longer to get to 1. Now let's say I take ln of 3 pi over 2. That's about 1.55. So that's going to be about here. So it keeps rotating out, gets a little bit longer. About ln of 2 pi. That's about 1.84. That's closer to here. And how about we'll just jump straight to ln of 3 pi, and that gives us enough to get the idea here. It's about 2.24. Okay, and so I think you can see what's happening with this graph, right? Is that the natural log is an increasing function. So as your angle increases, the distance from the origin increases, and it creates this spiral effect. Okay. That's it for that one. Let's move on to another example. Okay, let's talk about tangents. So notice that r is a function of theta, and that x is equal to r times cosine of theta, and y is equal to r times sine of theta, and that dy dx is dy d theta over dx d theta. So if we want to find dy d theta here, then we can just take our value for y and apply the product rule to r times sine of theta. So when we apply the product rule, we get the derivative of r times sine of theta plus r times the derivative of sine, which is cosine. And then when I look for dx d theta, I take x, which is r times cosine of theta, and I apply the product rule here. So I get dr d theta times cosine of theta minus r times the derivative of cosine. Or I should say it'd be plus r times the derivative of cosine, but that's negative sign, so we just put the negative in front here. So if we want dy dx, we can just divide those two things like so. Now, one thing to note is that if you're looking for tangents at the pole, that is where r is 0, then you plug in r as 0, and this simplifies. The dr d theta would then cancel, and you get left with sine of theta over cosine of theta, which is tangent of theta. Now, of course, this does assume that the derivative isn't 0, because then we wouldn't be able to divide by 0 there. We're not too worried about that at the moment. Let's go ahead and dig into an example. So this question says, find the slope of the tangent line to the polar curve at the point specified by the value of theta. All right, well, in order to do that, I need to find out what dy dx is. So what's dy dx? Well, that's dy d theta over dx d theta. And here's the thing. There are so many formulas to try to memorize in this course that whenever you can get those formulas from first principles, that's the best thing to do, right? So I don't have to like refigure or memorize what dy d theta is, because I definitely know that y equals r times sine of theta, right? Like that's been in my brain for 4 classes in a row, essentially, at this point, or at least 3 classes in a row at this point. So if I know that y is that, then I can just write out that product rule myself, right? I don't have to memorize the statement of the product rule. That might even be kind of silly to do. And then my dx d theta, same thing. So the derivative of r times cosine plus plus r times the derivative of cosine, which is the negative sign. So I'll put the negative in front. Now dr d theta is the derivative of r here. The derivative of 2 is 0. Derivative of negative sign is negative cosine of theta. All right, so let's plug in dr d theta. That's negative cosine of theta times sine of theta plus r times, well, let's plug in r as well. We want to write everything in terms of theta, so that's 2 minus sine of theta times cosine of theta all over negative cosine of theta times cosine of theta minus r, which is 2 minus sine of theta, times sine of theta. Now, we want to take this at theta equals pi over 3. That's going to give us our slope. So negative cosine of pi over 3 times sine of pi over 3. And actually, let me just give myself more room. We'll just move this over here. Plus, and it's really easy to make a little mistake here. So try to be careful and keep track of what you're doing, because you can easily flip a sine to a cosine or miss a negative or anything like that. Okay. Cosine of pi thirds. That's 1/2. So this is negative 1/2 times sine of pi thirds. That's the square root of 3 over 2. Plus 2 minus the square root of 3 over 2 times 1/2 divided by negative 1/2 times 1/2 minus 2 minus root 3 over 2 times root 3 over 2. Okay, up top here, we've got a negative root 3 over 4 plus, and that 2 is 4 over 2 minus 3 over 2, so that's going to be 4 minus root 3 over 2 times 1/2. And in the bottom, we get negative 1/4 minus, and this 2 will become 4/2. So 4 minus root 3 over 2 times the square root of 3 over 2. Okay, now up top, we get negative root 3 plus 4 minus root 3 all over 4. Because when I multiply this 1/2, I get 1/4. So both fractions are over 4. So we'll put that whole thing over 4. And a similar thing's going to happen in the denominator, but let's be careful here. We're going to distribute this negative and the square root of 3. So I'm going to get negative 4 root 3. And then when I distribute the negative here, it's going to be positive root 3 times root 3, which is plus 3. And that's all over 4 as well. Let me write that a little better. Now we know when we're dividing fractions, we multiply by the reciprocal, but that's going to lead to these 4's canceling. So we'll skip that step. And here we've got negative root 3 minus root 3. That's minus 2 root 3 plus 4 over. Negative 1 plus 3 is 2 minus 4 root 3. And you really don't need to simplify, but I'll do one thing, which is both of these have a common factor of 2. So I'll just pull that common factor out. Those cancel, and we get left with 2 minus root 3 up top over 1 minus 2 root 3 on the bottom. Okay. We're almost done here. I know this is quite a bit of a long one. Find the points of the given curve where the tangent line is horizontal or vertical. Okay, so when is the tangent line horizontal? Well, that's when the y values aren't changing. So it's horizontal when dy dx is 0. But in this case, we can actually just say when dy d theta is 0. Because we can think, hey, if the angle is changing but the y values aren't, then the line is, the tangent line is going to be horizontal there as well. But if we think about it that way, it does make things simpler, but we have to keep in mind that dx d theta can't be 0. So when dy d theta is 0, but dx d theta is not. Okay, that's straightforward enough. What about vertical? So we get a vertical tangent line when the opposite happens, when dx d theta is 0. But dy d theta is not. Now, what do we do if both dy d theta and dx d theta are 0? Then we actually would have to take a limit on dy dx so that we can solve for the limit from the left and right as the point travels along the curve. We'll see if we have to deal with that in this example, but most of the time we can just look at these two separately. Okay, let's go ahead and dive in. So since first we want to deal with when is dy d theta 0, we need to know what y is. Well, y is r times sine of theta. So that's e to the theta times sine of theta. And so dy d theta is what? So derivative of the first, that's e to the theta times sine of theta, plus the first times the derivative of the second. That's e to the theta cosine of theta. Notice I didn't actually use our derivative formula here, but it's the same thing, right? Like I didn't actually use the formula. I just wrote out what y is in terms of theta, right? And then took the derivative. Of course, it's the same thing, right? Okay, so I want to know when is this 0? Okay, good question. Well, that would be when e to the theta sine of theta equals negative e to the theta times cosine of theta. Now, since e to the theta can never be 0, we can divide that out and cancel. And that means this is only going to happen when sine of theta is equal to negative cosine of theta. So what angles will that occur for? Well, sine and cosine are negative of each other at 3 pi over 4, 7 pi over 4, 11 pi over 4, so forth and so on. In fact, they are negative of each other every time theta is 3 pi over 4 plus some integer multiple of pi. Now we want to make sure this doesn't before we figure out what our points are, where our tangent lines are horizontal. We want to figure out if there's any places where dx d theta is 0. So let's look at that first. So x is r times cosine of theta, which is e to the theta times cosine of theta. So dx d theta is e to the theta times cosine of theta minus e to the theta times sine of theta. So in this case, this will equal 0 when cosine of theta is equal to sine of theta. That means theta is pi over 4, or 5 pi over 4, or 11 pi over 4. Not 11 pi over 4, 9 pi over 4. So forth and so on. So in other words, when theta is pi over 4 plus any integer multiple of pi. And those two sets of solutions don't overlap, so we have no problem there. So since our r value is e to the theta, that means our points are going to be e to the 3/4 of pi plus n pi. And then the theta coordinate is 3/4 of pi plus n pi. And so we could call these, we could give these the formula Pn, P sub n. So there's a different point for every n value where this line, where this curve will have a horizontal tangent line. And similarly, Pn for the vertical tangent lines will be e to the pi fourths plus pi n, and pi fourths plus pi n. Okay, yeah, again, I know that was a long one. Thanks for sticking it out, and I hope you all have a great day. Thanks for watching.